Picture the night sky as a quiet airport, and every planet, comet, and asteroid follows the usual lanes. Then one evening, the control tower spots a streak that is not lining up with any runway, not obeying any local traffic pattern, and definitely not here for the duty-free. That is 3IATLAS, an interstellar traveler barreling in on a path that does not circle our sun, but slices through the solar system like a needle through fabric. Right away, astronomers sit up. This is not a local, this is a passport stamp from somewhere we have never been. Why is that a big deal? Because most of what we know about other solar systems is either light years away or filtered through the thin clues of starlight. Here, for once, the universe does home delivery. An object forged beneath a foreign star wanders into our yard, and we get to watch how it behaves when our sun warms it, our wind pushes it, and our gravity tugs at it. It is like hosting an exchange student who arrives with a suitcase full of unknown snacks and a playlist we did not know we needed. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes, it's best enjoyed the way you'd enjoy a late-night conversation, quietly with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. The confirmation moment feels like drama, because it is drama. Observatories compare notes, check the motion, and realize the path is not a closed loop around the sun. It is open-ended, a come-through and keep-going route. The numbers spell out a simple truth in sky language. This object was not born in the dusty nursery that gave us Mercury through Neptune. It learned its manners under a different set of cosmic streetlights. Suddenly, the solar system is not just a family portrait. It is a train station, and a stranger has walked in. Interstellar visitors change our questions. With a regular comet from the outer deep freeze, we ask what recipe our own cloud of leftovers followed when the planets formed. With an outsider, we ask what recipes other kitchens used. Do other stars bake their comets with the same ingredients? Do they add extra organic spices or skip the salty minerals we take for granted? Space is basically the ultimate cooking show, and this is the episode where a mystery chef enters the studio. But there is more at stake than curiosity. When someone from out of town arrives, the whole city reacts. The sun's light may tease out gas or dust from the surface, and that stuff can dance with the solar wind in ways we have not seen before. Planetary magnetic fields may hum differently as the visitor plows through, and our instruments might catch new patterns. Even the quiet dust lanes and the thin interplanetary breeze can light up around a new traveler, the way a river riffles when a canoe slices through it. The solar system is not just watching, it is responding. This is also a story about speed and timing. Our local comets are like regulars who know when the coffee shop opens. They saunter in, warm up, flare a tail, and swing back out on a schedule. An interstellar object blasts through on its own clock. It might brighten fast, rotate oddly, or shrug off sunlight in a way that refuses to match the charts. That means we scramble. Telescopes pivot, networks ping, amateur observers join in. The cosmos has thrown a pop quiz, and everyone wants to show their work. Cue the human side, a quiet control room, midnight snacks, red lights glowing, and someone whispering, "There it is." And then the flood of data begins. There is the satisfying click when the path prediction and the next snapshot line up. There is the nervous humor that keeps scientists sane at 4 in the morning. Black holes are the universe saying delete browsing history permanently. Interstellar comets are the universe dropping into your group chat, uninvited, and somehow becoming the main character. Of course, the big backdrop is origin. Where could 3IATLAS have started? Maybe a young system where planets were still elbowing each other for room. Maybe a distant star that swelled, sneezed, and tossed out debris like confetti. The object could have spent ages wandering a cold, silent highway between stars, only to turn a corner and find our sun shining ahead like a neon diner at the edge of a dark road. That image matters because it reminds us that space is not empty of stories. It is just quiet until something crosses the microphone. And here is the twist worth savoring. By watching a single outsider, we refine our understanding of insiders. When we compare how our comets act to how this one acts, we sharpen the outlines of what is normal for our neighborhood. If it behaves wildly differently under the same sunlight, great. We just learned that planet building can take many roads. If it behaves almost the same, that is also great because it hints that the rules of making small worlds rhyme across the galaxy. Either way, the lesson is a win. Curiosity is the only currency that appreciates even when the market crashes. So welcome, 3IATLAS, to our busy little cul-de-sac. We will not keep you long, and we cannot promise the coffee is good, but we will absolutely point every instrument we have at you and ask polite questions with breathless excitement. Because this is not only about what you are, it is about what your presence does to us. It snaps our heads up, widens our mental map, and reminds us that our solar system is not a sealed box, but a crossroads on a much larger road. Next time, we will pull back the curtain on how we know this traveler is not from here, tracing the fingerprints in its motion and the clues in its path that shout outsider with absolute confidence. Chapter 2. How do we know it is not from here? Imagine you are a tracker, following prints in fresh snow. Local animals leave loops and zigzags that start and end in the same forest. But one morning you find a long, confident line that slashes straight across your land and disappears into the horizon. That is the vibe of 3IATLAS. Its path is not a loop, it is a passing line. Astronomers do not just see dots of light, they read those dots the way detectives read footprints, asking the same basic questions. Where did it come from? How fast is it going? And will it ever come back for breakfast? First, the shape of the path. A homegrown comet, or asteroid, is bound to the sun. Bound paths are ovals of many flavors, from roundish to stretched, but they are still ovals. If you had a pen on a rubber band, it would always snap into a closed curve. An interstellar visitor tells a different story. Its path opens outward like a wide U that never closes, the way a stone skips across a pond and keeps going instead of settling in. That open shape is the calling card of a traveler that the sun cannot keep. When astronomers fit all the nightly positions with a best path, the math whispers one simple sentence in sky language. This is not a local loop. Now the sprint versus stroll test. Anything born here started slow compared to the vast pull of the sun. Even when nudged by planets, local objects move in ways the sun can still shepherd. Interstellar objects arrive already moving with the momentum of their old star neighborhood. When we measure their speed far from the sun, before warming and outgassing complicate the picture, we sometimes find they are already moving too quickly to be adopted. Think of the sun as a generous host with strong arms. Most guests can be guided to stay for dinner. A few sprint through the doorway and out the back before the host can say hello. How do we get these answers from a handful of faint dots? Step 1 is timing. Telescopes take images minutes apart, hours apart, nights apart, and even weeks apart. The intruder shifts against the background star field in a way that tells us how fast it is slicing across our line of sight. Step 2 is the parallax dance. Earth is constantly moving along its own path around the sun, so when we observe the visitor from different points on that path, the object appears to wiggle. That wiggle is precious. It lets astronomers triangulate distance in the same way your brain uses two eyes to judge depth. Step 3 is the color and brightness routine. As the object turns and tumbles, sunlight reflects differently. The way the brightness rises and falls across many nights hints at the shape and spin. If the object brightens faster than a typical local comet at the same distance, that can be a clue that it has a surface that wakes up differently under sunlight. But the key evidence for origin still lives in the path. Track the dots carefully enough, and you can extend the line backward in time to see where it aimed from, and forward in time to see where it will head next. When both ends refuse to bend into a loop, the verdict is in. There is also the sun's escape test, explained in plain terms. Picture a hill with a deep valley. Local objects are kids playing in the valley. They roll up the side, but never crest the top unless something gives them an extra kick. An interstellar object arrives already near the top edge of the hill. Even before it feels much of our sun's pull, it is high on energy. It drops in, swings by, and climbs out the far side without losing enough steam to stay. The exact numbers live on chalkboards, but the story fits in a single sentence. It is moving with more get up and go than the sun can cancel. The detective work also includes a check for optical illusions. Maybe it looks like a straight line because our data are too sparse. Maybe it looks fast because we misjudged the distance. Astronomers handle this by collecting more nights of positions from as many telescopes as possible, on as many continents as possible. Northern skies, southern skies, mountaintops, sea-level domes, even backyard gear with careful timing can help. Each new dot tightens the path until the open shape is undeniable, the way a connect the dots drawing turns into a picture you cannot unsee. Here is the spicy twist. What if this is not rare at all? Our technology has only recently turned many eyes to the sky every clear night. For most of human history, we scanned with the two cameras attached to our faces and a handful of glass lenses. Small dark objects could have blazed through the inner system unnoticed, the way a midnight cyclist slips through a quiet street without waking the neighborhood. There are blind spots too. Objects that skim near the glare of the sun are incredibly hard to spot. Some dip below the horizon for entire continents. Weather closes domes. The sky is big. Our eyes are finite, and the universe has plenty of patience. As surveys speed up and software grows sharper, we are starting to pick up fainter, faster, and weirder visitors. If you imagine the solar system as a porch with a motion sensor, we have only recently upgraded from a light that flickers on once in a while to a smart system that pings your phone every time a moth flutters by. It raises the delicious possibility that countless silent travelers cross our yard every century. Some are pebbles that whisper. A few are mountains that hum. Most slip through without so much as a hello. So how do we know 3IATLAS is not from here? Because its footprints do not loop. Its sprint is too peppy for a lifelong stay. Its path, when extended backward and forward, reads like a road that starts beyond our fence and ends beyond the opposite fence. The case is not closed by a single clue. It is closed by a pattern that refuses to be anything else. The detective looks at the snow, smiles, and writes in the notebook, "Visitor, not resident." Next up, we shift from the logic of paths to the choreography of pursuit. How sky surveys, rapid alerts, and a global relay of telescopes turned a faint discovery into a full identity card. Chapter 3, First Contact, with telescopes. Before anyone points a spacecraft, the first handshake happens with glass and silicon. Night after night, wide field surveys paint the sky onto digital canvases. Not once, but many times, like a flipbook. The trick is simple, in spirit, and heroic in execution. Take an image, wait a little, take another, and let software hunt for anything that nudged between frames. Stars stay put like ceiling pins. The interesting bits are the wanderers that drift a hair to the left, a whisker to the right, or brighten as if whispering, "Look at me." Space does not announce itself with fanfare. It leaves breadcrumbs. Telescopes are our patient breadcrumb readers. A modern survey is less a single telescope and more a choreography. There is a scheduler that decides which patch of sky gets attention, a weather mind that values clouds, and a camera that gulps photons through a mosaic of sensors. Each exposure is a splash of starlight, divided into millions of tiny wells. When the shutter closes, all those wells report in. How much light did they catch? What color did it lean toward? Did anything saturate or trail? If an exposure is a heartbeat, a night of observing is a pulse train. The sky is alive in that rhythm. Now the pipeline goes to work. First, clean the image. Subtract the sensor's own hum, divide out tiny quirks in sensitivity, and align the pixel grid so that the same star lands on the same spot across the night. Then comes difference imaging, the art of subtracting tonight from a crisp reference. What remains are changes: supernovas blooming in distant galaxies, asteroids pacing across the yard, satellites photobombing like overexcited tourists, and once in a while, the faint wanderer that does not match any catalogue. The computer does not care about romance, it cares about thresholds and statistics. But to the human at the console, that first clean residual is a tiny gasp. Discovery is basically curiosity, with good exposure control. No one trusts a single frame, so candidates go through a gauntlet. Are they cosmic rays punching single-pixel bruises? Are they ghosts from a bright star just off the edge? The vetting software trains on thousands of fakes and thousands of real objects until it can separate sparkle from speck. The survivors earn a ticket to the alerts queue. Imagine a global fire hose of small, structured messages. Here is a thing that changed. Here is where it lives on the sky. Here is how bright it looked. Here are the last few sightings. Those alerts ripple through observatories, like texts in a group chat. When someone shares a rare rainbow, observers call this the marshalling phase. I call it science speed dating. You have seconds to decide if you want a second look. Follow-up telescopes take the baton. Some are nimble robotic scopes that can slew from one horizon to the other faster than you can say night mode. Some are big mirrors that need gentle coaxing but reward patience with exquisite detail. They cross-check position, refine motion, and gather spectra, which is a fancy way of saying they split light into a barcode that hints at composition. One instrument measures how the object brightens with changing angles of sunlight. Another watches for subtle flickers that betray a spin. Data does not just pile up. It becomes an identity card: name, last seen location, tendency to brighten or fade, likely family, and whether it is worth waking the veteran observers in the next time zone. The human dance is just as intricate. A survey team posts a candidate. A network of amateurs and pros claim follow-up slots. Cloud cover wrecks one plan and forces a backup. Somewhere, a grad student sprints for a dome key. Somewhere else, a remote system in a desert pings a supervisor. I have it, confirmation locked. People imagine astronomy as solitary nights and quiet note-taking. In truth, it is a relay in the dark, and the baton is a stream of numbers. Here is where the speculative curveball lands. What if we build a system that can pass targets from ground to orbit, like a relay team that never drops the stick? Picture a lattice of small, smart satellites, each with a wide view and a taste for motion. A ground survey flags a mover and pings the network. The nearest satellite swivels, grabs a quick set of images above the weather and the glow of cities, and returns a sharper path. A second satellite primes a tiny spectrograph to sniff the sunlight bouncing off the intruder. A third pushes the data to a processing hub that updates predictions in real time. No more waiting for dawn, no more losing a faint visitor behind a mountain or a storm. Space becomes its own lookout tower. In that same future, software agents act like dispatchers. They compare new alerts to all known objects, simulate 100 possible paths for the next few days, and recommend the next move. Telescopes on ice fields, desert plateaus, and ocean islands listen to the same digital conductor. Each instrument knows its strengths and limitations. This one is a sprinter for quick snapshots. That one is a marathoner for long, deep exposures. The network becomes a living thing that assigns jobs not by habit, but by opportunity. It is logistics, but with starlight. Even the way we store and share the flood of observations is changing. A discovery is only useful if the right people can act on it, while the trail is still warm. That means standardized formats, open dashboards, and robotic cues that will bump a target to the front of the line when it matters. The glory moments are still the images, but the unsung hero is the metadata. Time stamped against atomic clocks, pointing directions nailed within a hair. Uncertainties measured, not guessed. Precision is the difference between a rumor and a rendezvous. First contact with telescopes is not a single click. It is a layered conversation between photons and people, sensors and scripts, hunches and hard checks. The romance lives in the first hint of motion. The reliability lives in countless comparisons that follow. When it works, the result is a clean handoff from discovery to characterization to prediction, so that by the time the visitor approaches the inner lanes, we already know where to watch, what to measure, and how not to blink. In the next chapter, we step beyond the cameras and into the weather of space itself, watching how the steady breath of the sun meets a stranger and writes bright signatures across the dark. Chapter 4: The Solar Wind Meets a Stranger. Think of the sun not as a distant light bulb, but as a star with opinions, and those opinions blow constantly. A stream of charged particles and threaded magnetic fields rushes outward in every direction, day and night, like an invisible ocean current that never tires. Astronomers call it the solar wind, but do not let the polite name fool you. This is space weather with attitude. Now picture 3IATLAS as a dusty, icy ridge drifting into that current. When wind meets ridge, you get patterns, waves, eddies, bright crests, and long tails. Mountain weather, but in vacuum. Start with a steady breeze. Even on a calm day, the sun exhales particles fast enough to lap the planets, carrying magnetic strands that spiral outward like a slow twist of taffy. The wind is not uniform. It has slow lanes and fast lanes, quiet patches and gusty ones. Sometimes the star sneezes, and a coronal mass ejection surges out like a pressure wave. Other times it hums along, gentle enough that dust can dance. Into this comes the stranger, cold surface warming for the first time under our star, releasing gas and tiny grains like a dry sponge meeting warm breath. The object does not have to try. Sunlight does the coaxing, and the wind does the sculpting. At the leading edge, where motion and wind collide, a boundary forms that behaves a lot like the air pileup in front of a mountain. Particles slow, heat, and deflect. The magnetic field lines, carried by the wind, drape around the object's expanding cloud, the way streamers bend around a car's windshield. That draping matters. Charged particles prefer to slide along those lines rather than cut across them, so paths warp and funnel. It is the difference between hiking straight up a slope and finding a switchback that lets you keep your breath. The result is a layered structure, a four-region, where the wind grows choppy, a transition where things get messy, and then the inner cloud where gases from the intruder dominate. Within that inner cloud, new players emerge. Neutral atoms shed from the surface can steal electric charge from the wind's particles in a kind of cosmic handshake gone sideways. The newly charged newborns pick up ions, are grabbed by the magnetic field and whipped into motion. They spiral, they energize, and they can feed waves that ripple outward. If a mountain could somehow teach the air to whistle as it passed, you would hear something like this in plasma form. These waves can, in turn, alter the flow of the wind itself, creating a feedback loop where the object reshapes the very conditions that are shaping it. Then there are the tails, not one, but often two, each with a different personality. The dust tail is the scenic one, a broad sweep formed by sunlight, gently pushing tiny grains away. It curves like a ribbon and cares more about light than magnetism. The plasma tail is the showrunner for space weather fans, a narrow, straight beam guided by the magnetic field lines in the wind. If the wind shifts, the plasma tail snaps and realigns like a windsock caught by a sudden gust. Occasionally, when a strong solar puff passes through, that tail can even disconnect, a dramatic flick like the universe trimming a kite string, and then grow again as the field settles. Space has better special effects than any studio. It just plays them slowly. All of this is not just pretty. it is diagnostic. By reading how wide the interaction region grows, how fast the tails respond, and which wavelengths flare, you can infer how much gas the object is shedding and how the wind is behaving upstream. The stranger becomes a probe that does not need a power cord. We are used to thinking of comets as things to be observed. Here they are, instruments written by another star, logging our star's breath as they pass through it. The mountain weather analogy holds in another way. Topography matters. A lumpier, more fractured surface can release gas in jets, creating little thrusts that puff the cloud into uneven shapes. The wind catches those asymmetries and exaggerates them, much like a hillside funnels fog into fingers that reach down a valley. Over hours and days, these fingers can precess and wobble as the object spins, carving spirals and fans that tell a timekeeping story. If you ever wanted a clock made of vapor, dust, and magnetic spaghetti, this is your moment. Now imagine taking this dance and plugging it into a forecast. Space weather already matters to satellites, power grids, and radio systems. Add a transient visitor, and suddenly there is a new variable. A short bulletin could read, "Fast wind, overtaking the interstellar object tonight. Expect enhanced tail activity and increased pickup ion flux downstream." It sounds niche until you realize that every mission planning to observe the visitor wants that heads up. Every radio telescope cares about the bursty environment, and every student hoping to catch a rare tail disconnection needs the timing. Interstellar object advisories are basically storm warnings for the curious. Speculate a step further. Tomorrow's observatories could run a live traffic map of the solar wind, merging satellite readings with models, then overlay the predicted path of visitors. When a gusty spiral arm of the sun's field threatens to smack into the intruder, the system nudges small telescopes to watch for tail kinks, pings particle instruments to gather counts, and tells image processors to brace for fast changes. This is not only about seeing something cool, it is about learning how a star's breath behaves when it meets new shapes. The visitor gets a free ride. We get a new set of fingerprints. Through it all, remember the tone of the cosmos, patient, intricate, and occasionally cheeky. The sun blows a continuous stream like a hairdryer that never cools, and the interstellar object answers by turning that breeze into sculpture. Earth is basically a rock that won the cosmic lottery. Today, the jackpot includes front-row seats to wind art in vacuum. If mountain weather could post time-lapse selfies, it would look a lot like this. In the next chapter, we stop looking at waves and wind and start sniffing ingredients. What rises off a warming surface, which molecules paint the glow, and how a foreign recipe might surprise a solar system with a very particular palate. Chapter 5. Chemistry Without a Passport. Picture the nucleus of 3I/Atlas as a deep-freeze pantry rolling through the dark, lids sealed, labels long faded, then it drifts into sunlight, and the pantry starts to breathe. Ices in the surface layers warm and leap straight from solid to gas, dragging dust grains along like hitchhikers clinging to a departing bus. The quiet rock becomes a fizzy fountain. It is not dramatic by human standards, no roaring flames, no crackling soundtrack, but in the language of space, this is a full-blown festival. Photons show up like paparazzi, and the chemistry poses for portraits. Different ingredients wake at different distances. Water ice snaps until it feels a decent dose of warmth, then vents in steady plumes. More skittish species, such as carbon monoxide and methane, can turn on farther out, like early risers, who start making coffee before dawn. Carbon dioxide, ammonia, and a menagerie of organics join in as the surface layers loosen. Each ingredient leaves a spectral autograph, narrow colors sprinkled across the light, that tells observers not only what is present, but roughly how much is pouring into space each second. The nucleus does not need a label maker. Sunlight writes the inventory in glow. Once in the coma, the fresh gases do not stay themselves for long. Sunlight splits and rearranges them the way a chef chops and sautés. Water becomes fragments like hydrogen and oxygen that race outward. Organic molecules crack into simpler pieces that shine in their own distinctive hues. Some fragments, like the one that gives off a famous blue-green tinge, are not lingering residents of the nucleus at all. They are short-lived children of parent molecules broken by light. If the coma is a kitchen, photochemistry is the sizzling pan where raw ingredients transform into aromas. Dust adds texture to the recipe. Grains range from powdery smoke to pebble-sized bits, each with its own personality. The tiniest grains scatter blue light more efficiently, giving parts of the coma a cool tint. The larger particles reflect sunlight with a warmer, creamy sheen. Because dust does not respond to magnetic fields, it spreads and curves under the slow push of sunlight and the momentum of the nucleus. In polarized light, light with a preferred direction, the dust can reveal shapes and surfaces, telling us whether grains are fluffy clumps, smooth chips, or something in between. It is cosmic makeup analysis without the influencer drama. What makes an interstellar visitor tantalizing is not just the grocery list, but the ratios on that list. In our local comets, we have a library of how much water typically accompanies carbon dioxide, how often we see certain sulfur compounds, how rich the organics tend to be, and how those numbers change with sunlight. If 3I/Atlas matches those ranges, that whispers that chemistry in planet-forming disks may rhyme across the galaxy. If it refuses to match, if, say, it carries unusually generous amounts of carbon monoxide or reveals rare nitrogen-bearing organics at surprising levels, then we have a postcard from a kitchen that seasons differently. Isotopes turn the plot from good to great. The same element can have heavier and lighter versions, and the proportions of those versions carry a memory of temperature, radiation, and time. In our own neighborhood, water in some comets holds a heavier to lighter hydrogen balance that hints at where and when that ice formed. If an interstellar traveler arrives with a balance wildly outside our local range, it would be like tasting a familiar dish and realizing the salt is actually a mineral you have never had before. Suddenly, the origin story bends. Maybe its nursery cloud was colder. Maybe its star bathed it in harsher ultraviolet. Maybe its grains cooked longer before being sealed in ice. Sunlight not only paints, it pushes. The pressure of light acts gently but relentlessly on small grains, sorting them by size like a careful librarian. Over hours and days, that sorting makes bands and fans, especially if jets from the nucleus switch on and off as it spins. Jet chemistry can differ by patch too. A crater rim rich in carbon dioxide will launch a different bouquet than a flank loaded with water ice and dark organics. As the nucleus rotates, those bouquets braid into spirals, slow-motion fireworks that let us clock the spin period while sniffing which patch served which scent. Now for the delicious what if. Suppose we spot a molecule that has never been confirmed in a comet, something elaborate that usually forms on dust-grained surfaces in extremely cold, shielded places, perhaps a sugar-like building block, or a fragile ring that dislikes heat, or a chain that suggests a very specific assembly line. Detecting it would not mean life, full stop. That is a separate, careful conversation, but it would imply that the raw pantry for life can be assembled in more places, under more conditions than we assumed. Planet formation models would have to make room for richer pre-seasoning. The origin stories of atmospheres would need a rewrite to include these extras, arriving by gentle delivery, not just by violent impacts. Even a quieter surprise could rattle our frameworks. If we find that oxygen trapped in the ice is freer than expected, or that sulfur compounds are strangely muted, it could tell us about ultraviolet lamps in the object's birth cloud, about how long it basked in cosmic rays, or about whether its dust grains were coated with layers that changed the surface chemistry before everything froze. Chemistry is a historian with a magnifying glass. Every ratio is a footnote about the past. Of course, we keep our sense of humor. A cometary coma is basically a perfume counter with questionable ventilation. You wave a spectrograph through it, and the air tells you its secret. Earth may be the rock that won the cosmic lottery. Interstellar chemistry is the fine print on the ticket that says, by the way, your neighbors play with exotic flavors. As 3I/Atlas recedes, the glow fades, the kitchen cools, and the pantry doors close again. But the ledger remains, a set of lines and colors that say, here is what warmed, here is what flew, here is how sunlight painted the air. Next, we step from ingredients to choreography, watching gravity's quiet hand shape the visitor's passage like a conductor, guiding a once-in-a-lifetime performance. Chapter 6, Gravity's Welcome Party Space, looks empty, but it is hosted by a very social force. Gravity is the friend who insists on a group hug, and when 3I/Atlas steps through the door, every giant planet lifts an eyebrow. The path may be set by where the traveler came from, but the vibe of the party changes as it threads past the big guests, the worlds with rings, the worlds with storms, and the worlds with enough pull to casually edit a trajectory that has been cruising for ages. This is the welcome party where the handshakes are invisible and unforgettable. Start with the idea of spheres of influence. Each planet carries around a neighborhood where its gravity outmuscles the sun's tug, at least for passing visitors. Picture bright porch lights cast into the dark. Step into one and you feel the owner's presence a little more. Our interstellar guest will not slow to chat, but even a brush with that neighborhood can leave a fingerprint. The closer the pass, the firmer the handshake. The farther away, the subtler the nudge. Gravity works on the honest principle of proximity. Nearer means louder. Now for tidal nudges, which sound like a beach vacation, but act like a gentle wrench. Gravity is slightly stronger on the side of a body that is closer and slightly weaker on the far side. That difference stretches things. For a compact, sturdy nucleus, tides mostly tug at the coma and the flight path, twisting the spin a whisper here, bending the route a whisper there. If the object drifts too close to any giant, tides can escalate into a stern warning. There is a limit. Cross it. And rubble piles, remember they are rubble. Think of it as the universe's version of do not lean too far over the balcony. Most interstellar visitors keep a respectful distance, but the warning exists, and it shapes their options. The headline act, though, is the gravitational assist. No rockets required, just a moving planet and a clever path. Imagine a high-speed jog past a moving walkway in an airport. If you time it right and step onto the belt at just the right angle, you leave with an extra spring in your step. Time it wrong, and you absorb some of the belt's energy in the opposite direction, leaving a little slower. In space, the belt is the planet's motion around the sun. Our visitor can steal or donate a sliver of that motion simply by skimming past on the correct side. To the planet, the trade is negligible. To the traveler, it can reshape decades of flight in a single afternoon. Here is where small tweaks turn epic. A minuscule shift in where the object enters a giant's neighborhood can set up a completely different exit. Miss by 1,000 kilometers, and you skim by, wave politely, and keep going. Miss by 1,000 kilometers in a different direction, and you carve a new path that crosses the orbits of other planets at new times. The system is full of resonant rhythms, no fly lanes of timing, where a returning pass lines up again and again with someone's porch light. Drift into those rhythms, and gravity can pump the trajectory like a kid on a swing. Small pushes at the right moment, adding up to big changes. Drift just outside, and nothing much happens. Chaos is not a disaster. It is sensitivity in a suit and tie. There are even tiny keyholes, narrow corridors in space that act like doorways to wildly different futures. Thread one, and the next encounter shifts from distant nod to close conversation. Miss it, and you vanish into the dark with only a postcard. For a mission planner, keyholes are opportunities and nightmares. For an interstellar object, they are fate, entered or avoided by the luck of initial conditions, written light years away. Cosmic billiards is not about smashing into pockets. It is about grazing cushions so precisely that a ball set in motion ages ago ends up somewhere no one expected. One tap today changes the table 3 million years from now. While threading the realms of the giants, our visitor also meets their extended families, moons, ring arcs, and shared dust. Pass near a moon's path, and you can get a miniature assist nested within the larger one, like a bonus round. Cross a ring plane, and the tiniest grains whisper against the coma, almost unmeasurable but not meaningless. Gravity choreographs the big steps. The small steps leave texture. Space may be quiet, but it loves details. Spin state is another hidden thread. A slight tidal torque can adjust the rotation, and that changes how jets of gas and dust point over time. Jets are like tiny thrusters. They breathe, they push, and they shift the track by drips. Over weeks, those drips add up. The giant's gravity is the conductor waving the baton. The object's own outgassing is the percussion section tapping along. Together, they write a rhythm you can read in nightly positions, each dot a note on a staff. The beauty here is practical. By mapping possible paths through each planet's neighborhood, astronomers can forecast not only where to point telescopes, but which instruments to ready. A close pass means high-cadence imaging, rapid spectra, and a sharp eye for spin changes. A distant nudge means a calmer plan, with attention on how the long arc shifts. Gravity teaches humility. You never truly own a prediction. You rent it until the next encounter. Humor survives even in precision. Space may not do punchlines, but gravity does have a sense of timing. Just when you think a trajectory is a straight shot, a planet steps into the crosswalk and tips its hat. Earth is a rock that won the cosmic lottery. Gravity is the rule that decides how our winnings arrive and how long they stay in the bank. By the time 3I/Atlas leaves the giant country, it carries quiet edits stamped into its path and spin. Souvenirs you cannot frame, but you can measure. Some edits are gentle curves, some are sharp turns that reroute a lifetime. The party ends without confetti, only a new direction and a subtle change in rhythm. Next episode, we focus on the heavyweight with the biggest guest list and the longest reach, exploring how one planet's oversized gravity can protect, redirect, or, on rare occasions, keep a souvenir for itself. Chapter 7, Jupiter's Big Brother Effect. If the solar system were a nightclub, Jupiter would work the door with a clipboard and an eyebrow that means business. The giant does 3 jobs at once. It shields the family from some rowdy drifters, it shapes the dance floor so the regulars keep their rhythm, and, on rare nights, it pockets a souvenir, an object that ends up orbiting as if the bouncer said, "You live here now." When 3I/Atlas skims the outer lanes, Jupiter is the presence you feel, even when you cannot see it. Gravity has a voice, and in Jupiter's case, it is a deep baritone that carries "Start with the bouncer" role. A lot of debris wanders the outskirts of the sun's domain, and some of it comes barreling inward like a late train. Jupiter's immense pull can intercept those trajectories, bending them away from the inner planets or flinging them onto long, sleepy routes that take forever to return. You can picture it as a giant hand gently palming a wayward marble. The marble still moves, but not toward the fragile glassware near the bar. It is not perfect protection. No cosmic guardian is, but it cuts down the number of direct gate crashes that would otherwise test Earth's patience and our insurance policy. Jupiter also shapes the entire layout of the asteroid belt. The way a careful architect uses sound baffles to sculpt how music flows through a hall. There are orbital sweet spots the giant's rhythm amplifies, and empty lanes it clears out over ages because the timing does not harmonize. The result is a belt with gaps and clusters, families and loners, all arranged by the metronome of one planet that never stops keeping time. Even objects that never meet Jupiter, face to face, still live in the neighborhood designed by it. Then there is the archivist role, which sounds like cardigans and quiet voices, but in space means a massive memory. Look at the troops of Trojan asteroids that march 60 degrees ahead of and behind Jupiter in its path. Those swarms share the giant's orbit, like companion floats in a parade, parked in gravitational parking lots, where the inward and outward pulls balance. Many were probably captured long ago and then curated by Jupiter's presence, held in place for billions of years. If you want a time capsule of the early system, those swarms are museum galleries with a spectacular view. Now and then, the bouncer and the archivist swap hats and become the occasional thief. Jupiter has a history of captures and breakups. A famous visitor once strayed too close and was torn into a chain of beads that later slammed into the planet in a show that wrote itself across the atmosphere. Other bodies have likely slipped into lopsided loops around Jupiter and stayed as irregular moons, a wild family with orbits that lean and tilt like a collection of mismatched chairs. The capture recipe is fussy. You need just the right approach, maybe a helpful nudge from a large moon, maybe a whisper of drag in the very top of Jupiter's vast envelope, or even a small push from the visitor's own gas jets at exactly the wrong or right moment. But when the ingredients line up, a free spirit becomes a resident. That brings us to 3I/Atlas and the game of alternate timelines. In one branch, it slides past Jupiter, outside the key corridors, tips its hat to the deep baritone, and coasts on. We take our measurements and wave goodbye to a traveler that keeps its independence. In a nearby branch, where the approach is shifted by a distance small enough to fit inside a city, the geometry changes. The object dips into the right slice of Jupiter's gravitational neighborhood and feels a tug at just the angle that steals a bit of its freedom. Add a tiny extra push from a jet on the sunlit side, no louder than a whisper compared with Jupiter's shout. And suddenly, the exit path does not lead to interstellar dark. It loops. Imagine the headlines in that timeline. A true outsider becomes a temporary mini-moon of the giant, perhaps for months, perhaps for years, tracing a stretched path that climbs and sinks, chaperoned by Jupiter's larger moons, like an entourage with clipboards. Every telescope with a pulse lines up to watch. We would track how sunlight changes the visitor's surface day by day, how tidal flexing warms specific patches, how the spin wobbles when it skims past a massive moon. If we are bold, we would push a small probe to rendezvous and tag the surface with a transmitter, turning a chance capture into a graduate course in interstellar geology. Most studied rock in history is not hype at that point. It is the only reasonable outcome. Even without capture, Jupiter can stamp the passport in memorable ink. A close swing by on the correct side can siphon a little of the planet's orbital energy into the traveler, sharpening its exit and changing the future places it will cross the sun's lanes, pass on the other side, and the traveler donates a sliver, leaving slower and heading into a fresh choir of orbits it would never have met otherwise. The exchanges are tiny compared to the giant's energy, but to the visitor, they are life-changing. Think of a camera shutter you tap with one finger, barely any force, and yet the entire image changes because timing is everything. Jupiter's moons complicate the whole scene in delightful ways. They are not silent ornaments, they are moving gravity wells of their own. A near miss with the largest moon can tweak the path as effectively as a main belt asteroid would, except it happens in the deep end of Jupiter's pull, where small changes get amplified. In a universe where details matter, these moon flybys are the fine print that decides whether a path curves into a loop or eases back to the open road. Through it all, Jupiter's personality stays consistent, generous with lessons, strict with timing, surprising when the geometry opens a door. Earth may be the rock that won the cosmic lottery, but Jupiter is the older sibling who keeps the neighborhood mostly safe, labels the storage boxes, and occasionally adopts a stray. If 3I/Atlas threads the giant's realm without a hitch, we still learn from the near miss. If it slides into a capture, even briefly, the entire field pivots to watch a once-in-a-lifetime residency. Next, we scale down the stage and shift to a red world with a thin sky and a lot of cameras, where front-row seats might catch dust and daylight clues that only Mars is positioned to see. Chapter 8. Mars gets a front row seat picture. A theater where the air is thin, the lights are sharp, and the ushers are robots with impeccable note-taking skills. That is Mars. On the night, an interstellar traveler glides through the neighborhood. The red planet does not have a thick blanket of weather to blur the view, and it does not have oceans to shrug off delicate signals. It is a lean laboratory with a clear window, perfectly placed to watch 3IATLAS write a brief signature across the Martian sky, and if we are lucky, sprinkle clues onto the ground. Start overhead. A thin atmosphere means starlight twinkles less, and faint streaks stand out more. When small bits shed from a visitor's coma dive toward Mars, they meet air that offers little cushioning. The result is crisp meteor traces, quick as a breath, bright enough for orbiters and rover cameras to catch on, carefully planned time-lapse runs. Up above, an orbiter can sweep long arcs of the limb, the curve of the planet's edge, looking for streamlined glows that reveal the altitude where grains start to burn. Down below, rover cameras stare into the dusk and do the patient thing. Click, wait, click again, building a flipbook of the sky. When one instrument records a blink at a certain moment and another records a streak at a slightly different angle, triangulation turns those blinks into paths. Mars becomes its own radar without needing a dish. Now pan to the instruments that drink in color. Orbital spectrometers can split the brief flashes into their component hues and recover a grocery list of elements freshly heated by entry. Surface spectrometers, tiny labs mounted on rover masts, can do the same trick for any powder that drifts down overnight. The fun is in the cross-check. If the sky says, "I saw a trace of a certain metal," and the ground says, "I found the same flavor in the morning dust," we have a link between the passing traveler and the sprinkle on the tablecloth. Mars may be rusty, but it is not confused. It knows when a seasoning is not from the house. Rovers add another sense: texture. Their close-up images can look at individual grains, nestled in cracks, and shielded corners where the wind is less bossy. Is the dust smooth like glass, frothy like ash, or a mix stitched together like crumbs of a brittle cookie? Grain shape tells a story about how that particle formed and what it survived. A pebble that was lightly baked under gentle warmth will round differently than a fleck that shattered away from a harder crust. The rover does not just look. It measures how grains clump, how they cling to a scoop, and how they charge under brushing. A laboratory with wheels can turn a single pinch of powder into 10 kinds of evidence. The planet's dryness turns out to be a feature. On Earth, a drizzle, a breeze, and a million busy microbes can remix a delicate layer before breakfast. On Mars, a whisper-thin frost at dawn and a modest afternoon breeze are often the whole risk. That means a faint dusting can sit on a panel or a deck plate long enough for careful sampling. Engineers watching power levels would grumble about the extra coating on solar hardware, but scientists would grin and reach for the toolkit. Sometimes the universe leaves your evidence on the windowsill. Orbiters, meanwhile, can sniff the edge of the atmosphere for temporary gases set free when grains vaporize or when fresh powder meets sunlight and warms. Think of it as a breath test for a planet. Today, the air carries a faint accent from a distant place. If two orbiters cross the limb at different local times, say one at early morning, one at evening, they can compare how quickly the accent fades. That decay rate helps separate truly foreign additives from normal Martian breath. None of this works without timing, and Mars has that covered too. Multiple assets share clocks, and Mars-to-Earth relays keep the schedule tight. An orbiter passes over a rover's site and pings a go signal. Point your camera now. The rover obeys, the orbiter records from above, and a ground telescope on Earth, yes, we will happily pull in help from the home team, adds a third perspective. You get a stacked dataset: sky flash, surface sprinkle, and a long-range track all at once. If science were a heist movie, this is the three-angle shot where everything clicks. What about the wind, that famous sculptor of dunes and dust devils? It is both a nuisance and an ally. In open flats, the wind will lift and smear any new layer quickly. In sheltered alcoves, it will deposit rather than erase. Mars is generous with microenvironments behind a rock, inside a shallow pit, under a rover's wheel arch where a fresh layer can hide until instruments arrive. Even the way the wind moves the new grains is a clue. Lighter, fluffier particles travel farther, denser bits huddle near their landing site. A rover can read that gradient like a treasure map. Now the speculative heart of the chapter, the faint dusting that only Mars can read. Suppose a barely measurable sheen settles out after the visitor passes. On Earth, that layer would vanish into pollen and rain. On Mars, it might linger on a lens cap or amassed in a thin, even film. A quick brush sample goes into a tiny oven and releases a bouquet when warmed. The profile could contain a ratio or a trace component that rarely survives in wetter, busier environments. Maybe it is a fragile organic fragment that prefers dryness. Maybe it is a metallic glass sliver that keeps its structure only when the air is stingy with water. Either way, the planet's quiet habits become a selective filter that preserves what would otherwise be lost. Mars turns into the perfect archivist, not by bulk, but by restraint. All along, we keep the tone that makes hard work bearable. Mars is that friend who keeps everything tidy and labels the jars. Earth is the rock that won the lottery. Mars is the neighbor who keeps the receipts. Together, they can tell a story that neither could alone, not just that a traveler passed, but exactly what it shed and how those crumbs behave when they land on a dry, cold world. From this red stage, we now pivot to a world wrapped in mystery curtains. Next up, thick clouds, hidden skies, and the strange ways Venus can notice a visitor without ever seeing the ground. Chapter 9, Venus and the Cloud Clues. If Mars is a tidy lab bench, Venus is a chemistry set, left simmering under a velvet curtain. The planet wears permanent overcast, like a diva's feathered boa, which makes traditional stargazing moves tricky. You do not get ground scenes. You get layers upon layers of cloud, stacked from the lower haze to the high deck where the winds sprint around the planet in a dizzying super rotation. For most visitors, that is a headache. For an interstellar traveler like 3I/Atlas, it is an opportunity, a chance for foreign dust and gas to brush a sky that is sensitive, reactive, and constantly remixing itself. The clouds complicate what we see, but they also become the instrument. Start with the challenge. Venus hides its surface light, the way a blackout curtain hides a window. Broad daylight wavelengths bounce off the cloud tops and blind us to deeper layers. But Venus also offers windows of its own making, narrow bands where thermal glow from the lower atmosphere leaks out on the night side, and ultraviolet contrasts on the day side, where mysterious absorbers paint blotches like ink in milk. Spacecraft and Earth-based telescopes key into those bands, taking pictures that are really medical scans, different wavelengths for different tissues. You do not look through the clouds. You learn the clouds by how they absorb, scatter, and glow. It is like tossing a drop of food coloring into a fast river and reading the current from the swirl. Spectroscopy is our lie detector. When gas from an interstellar coma brushes the top of the atmosphere, sunlight and thermal glow carve telltale lines into the reflected and emitted light. Instruments split that light and read the lines as if scanning a barcode. If a foreign ingredient is present, even briefly, its signature can ride along with the familiar set that Venus always shows. The signal might be faint, like a whisper at a concert, but repeated passes help. Watch long enough, and you can separate the steady Venus baseline from a transient accent. Space is not loud, but it is rhythmic. There is also the meteor trail angle, high, fast grains fizzing in the upper air and leaving behind layers of metallic ions that can alter radio wave paths. Venus has an ionosphere that behaves like a charged veil, and that veil is sensitive to new seed particles. A quick enhancement at a given altitude, seen during a radio occultation pass, when a spacecraft beams a signal through the limb to a receiver elsewhere, would look like a blip on a heart monitor. Old-school radio physics meets new-school cosmic sleuthing. Suppose a few grains actually make it into the main cloud deck. they would find themselves inside droplets that act like portable laboratories. Those droplets can pick up foreign bits, change size, and alter how they scatter light. Cloud microphysics, how droplets grow, merge, and settle, is fussy on Venus. Foreign dust could change the balance just enough to tweak the lifetime of a droplet, or the altitude where hazes form. Instruments that measure polarization, the preferred direction of light after it bounces, can read those tweaks because different particle sizes and shapes twist light in different ways. Think of it as sunglasses for planets. Rotate the lens, and suddenly hidden patterns pop. Ground truth on Venus is rare because, well, the ground tries to melt your robot. So the cross-check happens aloft and from afar. One orbiter watches the day side in ultraviolet to map absorbers, another stares at the night side, thermal glow to infer cloud thickness. Earth-based telescopes, when geometry allows, add high-resolution snapshots that track cloud motions with exquisite precision. If all three see a narrow band that was not there last week, and that band then stretches and thins on a timetable consistent with the superrotation, you have a case for a tracer. Not proof, but a pattern worth betting your next observing window on. There is a deeper chemical story lurking here. Venus's cloud deck hosts reactions that care about tiny nudges, a new surface for reactions. A stowaway grain with a different crystal structure could catalyze steps that are sluggish otherwise, temporarily shifting the balance among sulfur and oxygen-bearing species. That shift would echo in spectral features seen from orbit. Even if the foreign guests are few, they can be loud in the right choir. Planetary atmospheres are not just bags of gas, they are reactors with tunable knobs. Here is the speculative postcard. A tiny bit of interstellar dust falls into Venus's sky and acts as a tracer that drifts with the winds, darkening one ultraviolet swath for a week before the chemistry eats it. We map its journey around the globe, learn the exact tempo of the superrotation at multiple heights, and refine how droplets grow and fade. The visitor leaves no monument, just a lesson, how a thick, secretive atmosphere responds to a tap on the shoulder. It is like learning a city's transit system by following a single commuter with a bright umbrella. And because science deserves a grin, remember, black holes may be the universe's way of deleting browsing history permanently. But Venusian clouds are the pop-up blockers of the inner system. They hide everything, until the very moment they reveal exactly what you needed to know. Earth is the rock that won the cosmic lottery. Venus is the moody artist who teaches us to see by not letting us look directly. Next up, we pivot to our home air, where a planet with weather, oceans, and a billion sensors turns its entire atmosphere into a listening device. Earth's atmosphere, as a sensor, is not just a phrase. It is a full toolkit, ready for a rare performance. Chapter 10, Earth's Atmosphere as a Sensor. If you want a planet that eavesdrops well, pick the one with oceans, thunderstorms, and way too many cameras. Earth turns curiosity into an extreme sport. When an interstellar traveler like 3IATLAS swings through, our entire atmosphere can act like a microphone, a prism, and a notepad, all at once. The sky is not just scenery. It is a laboratory that covers the whole planet and never asks for overtime. Photosynthesis is plants' way of saying we invented solar panels first. Now our sensors want in on the bragging rights. Start with the most dramatic handwriting, meteor trails. When tiny fragments drift off the visitor and hit our air, they write bright lines that fade like chalk in wind. Those lines are not just fireworks, they are chemistry in motion. As a grain plows through the upper atmosphere, it heats, vaporizes, and leaves behind a column of excited atoms and molecules that glow with very specific colors. High-speed video cameras, scattered across continents, can triangulate the path of each flash, pin down its altitude, and measure how quickly it fades. From that, you get grain size, entry speed, and a first hint at composition. It is like reading the burn marks on a stovetop and guessing the recipe. Then, we split the light, spectrographs on professional observatories, university roofs, And yes, backyard setups with diffraction gratings all do the same magic trick. They turn a streak of light into a barcode. Each bar, each line is a clue. If you see features that match metals liberated from dust or faint signatures from volatile fragments, you are sniffing the pantry of the traveler without leaving the ground. Even when the meteors are too small to light up the sky, sensitive spectrometers can catch the afterglow in the upper air, a faint whisper at particular colors that lingers for minutes. The atmosphere becomes a memory foam pillow, recording the shape of what pressed into it. Polarization adds the fine print. Light that bounces off tiny grains gets subtly lined up in a preferred direction. Polarimeters measure that alignment, and the pattern changes with grain size and texture. Spread a lot of small, fluffy dust, and you get one kind of polarization map. Sprinkle larger, glassy bits, and you get another. Networks of polarimeters, from mountaintop stations to instruments that fit in a backpack, can map those patterns across the sky and tell whether the dust is more like ash or more like glitter. It is the difference between a whispering snowfall and a slow confetti storm, and the sky will tell you which one you got if you ask politely. Radio and radar join the chorus. The column of ionized air left by a meteor reflects radio waves just enough that even modest antennas can hear it. Amateur radio operators listen as signals ping off those transient trails, turning meteors into brief mirrors. Count the pings, measure their fade times, and you learn how dense the trail was and how quickly the atmosphere is recombining. Large facilities can ping the upper air on purpose and watch echoes drift with the wind, mapping where the debris is spreading. Space may be quiet, but our ionosphere throws a pretty good after-party. What makes this truly planetary is the network. Professional surveys flag times and directions. University teams deploy portable rigs in the right valleys and deserts, and citizen scientists fill in the gaps with backyard telescopes, doorbell cameras tuned to the night, and all-sky lenses that stare without blinking. A parent in pajamas can catch the same streak as a research observatory on a mountain, and both files end up in the same database by breakfast. The secret sauce is standardization. If everyone timestamps with care, calibrates color, and logs location, the modest gear becomes part of a giant interferometer built from good habits. Airplanes and balloons get in on the act. Commercial pilots sometimes report unusual glows in the upper air, and research aircraft with upward-facing cameras can chase predicted streams. Weather balloons loft tiny spectrometers into the middle atmosphere to sample the faint chemical echoes that follow a shower. The data are humble but invaluable. A bump here, a dip there, enough to say that something foreign brushed our air and left a fingerprint that the winds are now smearing into a larger shape. Oceans quietly archive evidence too. After major meteor events, collectors sometimes find microtektites and spherules in snow and shallow sediments. For a gentle drizzle of interstellar dust, the signals would be subtler, but specialized filters on research vessels constrain particle sizes and feed them to microscopes that read texture and trace elements. When a grain's composition looks out of family with typical Earth dust, the case grows stronger. The sea is a patient librarian. It files what falls. Satellites, of course, are the high gallery seats. Instruments that watch the limb of Earth can spot faint emissions at the edge of space, silhouettes of trails against the black, and polarization changes across large swaths. A spacecraft that maps night-side airglow will see temporary brightening where meteors have injected fresh energy. Pair that with ground reports, and you can reconstruct not just one streak, but the flow of a whole hour's worth of tiny arrivals. The best part is how these layers stack. A backyard polarimeter records a rise in alignment. A university spectrograph logs a faint line from a metal that fits interstellar dust. A satellite sees enhanced airglow along a matching path, and radio pings spike in the same window. Each signal alone is interesting. Together, they turn into a narrative, a slow, delicate rain from a visitor that may never come back. Science is a team sport, and the sky is the stadium where strangers high-five. Humor keeps us steady. Earth is a rock that won the cosmic lottery. We spend some of the winnings on eyes that never sleep. Photosynthesis claims the first brag on solar tech, but our senses are learning to flex. When a traveler wanders through, our planet does not just look up, it leans in and listens with every sense it has built. And as we file tonight's observations, we look outward again. There is a ringed world whose broad, bright bands act like a built-in detector. Next, we head to the planet with the jewelry, where even a whisper of alien dust might write its name in ice. Chapter 11, The Ringed Response. Saturn's rings are not just cosmic jewelry. They are an instrument the universe forgot to put back in its case. Imagine a circular orchestra of ice and rock, from grains smaller than sand to chunks the size of furniture, all orbiting in thin, disciplined sheets. When anything drifts through dust, grains, or the faintest whisper from a distant visitor, the rings do what good instruments do. They resonate, they scatter light differently, and they keep the memory longer than you would expect. In a solar system full of open skies, the rings are a billboard that updates whenever something sneezes on it. Start with how the rings see. Every ring particle is a little mirror with personality. Some are clean ice, bright as fresh snow. Some carry a thin patina of darker material, the way city snow looks after a day of traffic. When exotic dust falls in, it does not have to arrive like hail to make a difference. Even a delicate sift can tweak the way light reflects. Observers read those tweaks by watching how brightness changes with the sun at different angles. Look one way and you see a classic backscatter surge, as if the ring suddenly decided to flash its high beams. Look another way and forward scattering makes the ring glow like frosted glass. Add a new kind of dust, and those angle games shift. It is ring mood quantified. Color is another tell. Clean ice leans toward a certain cool tone. Weathered ice drifts warmer. Silicate dust nudges the palette in its own direction. Spread a trace of unfamiliar material, and the color ratios across a narrow ring zone change just enough to be noticed by patient instruments. Think of museum conservators shining different lamps across a painting to find underdrawings. Saturn's rings are that canvas, and dust is the sketch that a visitor leaves behind. Shape can tell a story too. The rings are thin in the vertical direction, but they are not truly flat. They carry ripples, wakes, and corrugations created by passing influences. A fine rain of fast dust can seed micro-disturbances that travel as gentle waves, nudging particles into patterns that were not there last month. Over time, those ripples drift, spread, and sometimes get shepherded by nearby moons into tidy lanes or ragged edges. A single gust does not remodel a beach, but it can set a small dune marching. In the rings, dunes are made of brightness variations and particle packing. Give it a dust analyzer that tastes chemistry from individual hits, an impact sensor that times tiny collisions like a drummer counting beats, a light meter that stares toward the sun and away from it to measure scattering angles, and a small radar to ping nearby swarms. The probe would feel the ring's micro-weather, sand grain impacts that arrive in flurries, electrostatic pops when plasma density shifts, whispering avalanches as particles rearrange along the edge. When an interstellar dust front sweeps through, the instrument suite would record a signature in layers. First, a rise in impact counts at certain speeds that do not match the usual local suspects. Then, a chemistry flag, a different mix of elements, or an unfamiliar mineral structure that says not born here. Next, a tweak in the forward scattering curve as new grains coat old surfaces, changing how they glint. Finally, a gentle propagating shift in the edge profile as sticky grains help particles cluster for a time before ring traffic rubs the effect away. It would be like hearing a distant truck, then smelling fuel, then seeing the dust plume, then watching the grass bend after it passes. Station keeping would be a ballet. The probe would surf weak gravitational gradients and use tiny burns to avoid getting drawn into denser streams, It might team up with a shepherd moon, hitching a ride on a co-orbital path that keeps it in the Goldilocks zone, close enough to touch the environment, far enough to keep its solar panels dent-free. A ring craft would not just observe, it would belong, moving with the ring's daily heartbeat. They are not walls, they are filters with attitude. When 3I/Atlas drifts through the neighborhood and sheds a breath of fast grains and faint gases, those capes feel it. The bubbles do not speak, but they do light up, hiss in radio, and rearrange their curtains of aurora, as if someone changed the soundtrack mid-song. Start with Earth's magnetic bubble, the smallest of our trio, but the most wired. On the sunward side, the solar wind piles up and slows, shaping a blunt nose where space weather first knocks. On the night side, the bubble stretches into a long tail that points away from the sun like a windsock at high altitude. The boundary of this bubble is a busy border crossing. Fields from the wind and from Earth can tangle and reconnect, opening brief doors. Through those doors, charged particles slide along magnetic highways that dive toward the poles. When they hit the thin upper air, electrons tap atoms and molecules like keys on a piano, and the sky answers with auroras. If the passing visitor delivers an unusual spice to the flow, the notes change. Imagine faint new colors or unexpected altitude bands, a hint that an ingredient not often seen has joined the party. Black holes are the universe's way of saying delete, browsing history permanently. Magnetospheres are more like pop-up blockers with pretty wallpapers. Now, scale up to Jupiter, where the bubble is so enormous it could swallow the sun and still have room for a snack. Jupiter's magnetic field is a heavyweight champion, and it spins fast, whipping plasma into a giant carousel. The planet's moons feed this machine, especially the volcanic one, whose outgassing creates a donut of charged material that rides the current like a neon racetrack. When the environment outside changes, the whole carousel adjusts its speed and brightness. A stream of foreign particles hitchhiking on the solar wind would not bulldoze a giant like this, but it could flavor the edges. The bow shock ahead of the planet might thicken, radio emissions might shift in pitch, and the glowing footprints where field lines link moon to planet could brighten or blur as currents strengthen. Jupiter's auroras already look like a fireworks show designed by an overachiever. A new ingredient could add strange tints at certain latitudes or tweak the rhythm of pulsing spots that beat like a metronome in the polar night. Saturn plays a subtler game. Its magnetic bubble is tidy, more aligned with its spin, and it hosts a delicate ring current that threads the system. The rings themselves shed tiny charged grains that mingle with the plasma, giving Saturn's magnetosphere a faint taste of ice. When the outer flow changes character, Saturn's bubble breathes, boundaries ripple, radio whispers grow louder, and auroral curtains widen or narrow as if the planet is adjusting its collar. A trace of exotic dust, or an unusual mix of volatiles passing through, could change how easily charge moves along certain lines, turning on or off thin arcs of light. Saturn's auroras tend to be elegant bands. Picture a new accent stripe appearing briefly, then washing away as circulation evens out. What does it mean for streaming material to thread these bubbles? Charged particles prefer to follow the lines rather than cross them. Think mountain hikers who choose ridge lines over bushwhacking. When the outer flow delivers a packet of fast, light ions from the visitor's wake, some of those riders will find lines that connect down to planetary atmospheres. They fall along the rails and deposit energy where the field says the rails end. The result is not a global storm, more like a set of highlights brushed into the usual picture. Instruments that watch in ultraviolet, visible, and infrared can separate these highlights by color and altitude, while radio ears listen for the hiss and crackle of changing currents. Each planet has its own tell. Earth's magnetosphere complains loudly when the wind turns southward in field orientation, an invitation for reconnection and a recipe for substorms. A flavored stream in that moment might push a wedge of new chemistry into the polar night, where high-resolution spectrographs could hunt for faint lines that rarely appear. Jupiter's tell is the mighty radio chorus that roars when the outer pressure changes. A careful ear could notice slight shifts in the chorus if the incoming particles carry a different mass mix. Saturn's tell is the graceful dance of auroral arcs around the pole. Extra charge along a particular set of lines could add a short-lived knot of brightness that rotates with the planet like a badge pinned to a spinning coat. Could auroras be tinted by unfamiliar chemistry? Magnetospheres are not passive shields. They are responsive galaxies of field lines and charged clouds, tuned to broadcast changes with beauty attached. Earth may be the rock that won the cosmic lottery. In magnetospheric terms, it won a programmable neon sign that lights the sky when the environment changes. Jupiter and Saturn own stadium boards. When a stranger passes and brushes the switch, all three may flash a brief foreign accent. We just have to be looking with the right eyes. Next, we trade glowing curtains for dusty heritage and ask a simple question with chaotic answers. How does a true outsider compare with our homegrown comets? And what happens to our models when the outsider refuses to play by the familiar rules? Chapter 13, Comet Culture Shock. Imagine inviting a traveler to a family reunion. Everyone knows the routine. Aunt Short Period arrives scuffed from repeat laps around the sun. Uncle Long Period shows up once in a lifetime with a grand tale and bigger stories, and the cousins from the outer cloud bring the usual mix of dust and drama. Then 3IATLAS walks in from another star and ignores the dress code. That is comet culture shock. The moment our expectations blink and we realize the house rules are not the galaxy's rules. Start with stage entrance. Homegrown comets tend to wake up in a familiar order. Far from the sun, only the jumpiest ices stir. Closer in, the dependable ones join the party. And by the time the comet is inside the giant planet's lanes, we get the classic look: a bright fuzzy coma, a dust fan that curves, and a straight, well-behaved plasma tail. Interstellar visitors can remix this timing. Some begin venting earlier than expected, as if surfaces built under alien starlight give up their gases at cooler temperatures. Others stay weirdly quiet until late, then sprint, like performers who refuse sound check and still nail the solo. The warm-up acts are telling. They point to what kind of ice sits near the skin, how porous the crust is, and whether sunlight sinks in or bounces off. Spin is another culture gap. Many local comets settle into a wobble pattern we have seen before, with jets acting like gentle thrusters that slowly adjust the dance. A true outsider might tumble in 3 awkward directions at once, changing brightness in a rhythm that refuses our tidy templates. That tumble matters because it steers which patches see morning and which stay in sunset forever, and that in turn sets the choreography of jets. If you are trying to forecast a light curve for a night of observing, a chaotic spin is the cosmic version of a cat on a keyboard. Shape also surprises. We have met local comets that are peanut-shaped, lumpy, or aggregated from boulders that barely hold hands. Those shapes come from slow construction in our own nursery and from countless warm passes that sculpt away the fragile bits. An interstellar nucleus might have been assembled in a different dust factory, under different pressures, then flung out early and kept in deep freeze for ages. The skin could be tougher, the voids larger, or the surface crust stranger. That difference shows up in how jets start and stop, how the coma feathers, and how the object responds to sunlight. Sometimes the curve of brightness with viewing angle looks off compared with familiar cousins, hinting at textures we have not catalogued. Dust tells a joke in a new accent. Local comets often release a predictable ratio of fine to coarse grains, giving the coma a specific sheen and the tail a familiar curve. Interstellar dust may be clumpier, more friable, or laced with minerals that change how it scatters light. The color of reflected sunlight can lean redder or bluer than average, not in a fashion sense, but in a mineralogical one. Think of it as finding beach sand that rolls differently underfoot, because every grain grew up in another ocean. Polarized light, when we measure it, can flip the punchline. The alignment and roughness that make our comets read one way suddenly read another, which means our size estimates and models need a fresh set of assumptions. Then there is the quiet engine beneath it all, the balance between dust and gas. Some local comets are dust scholarships, spraying grains with every sigh. Others are gas majors that jet with little grit. An outsider may live at a different point on that seesaw. If it is dust-rich, sunlight builds a thick shell that chokes off vents until pressure pops the lid. Hello, outbursts. If it is gas-rich with fine, slippery dust, the coma stays silky and the tail sharp, but tiny thrusts from uneven venting can shove the path more than we expect. Those tiny shoves are not magic. They are physics with attitude. We track the dots on the sky, night after night, notice a slight drift from the best purely gravitational path, and know the stove under the pot is set higher on one side. Now the question that makes chemists lean forward: what do the molecules say? Our local library contains the usual players: water, carbon-bearing gases, a mix of nitrogen species, and a pantry of organics, from simple chains to modest rings. Their ratios vary, but stay within ranges that tell a coherent origin story for our disk. An interstellar comet could walk in with a different menu. Perhaps it is heavy on a carbon monoxide cousin, light on certain sulfur flavors, or shows off a fragile molecule that usually tears apart before we notice it at home. Even one such detection would ripple outward. Disk chemistry models would need to allow colder shelves, different grain coatings, or alternate pathways for building complex organics on dust surfaces. Planet formation would inherit new starting conditions, and atmospheric recipes for brand new worlds would change their spice mix. A single grain could be the plot twist. Picture a speck trapped in a collector on a high-altitude aircraft, or embedded in an aerogel tile on a fast flyby probe. Under a microscope, it reveals layered ice with trapped organics arranged in a way that implies long, gentle cycling on a dust grain inside a distant cloud before freezing hard. Maybe the grain carries a handedness bias in one molecule, the kind of asymmetry life later amplifies, or a mineral inclusion that points to a different radiation history than our comets ever faced. That one speck would not prove life, but it would widen the stage on which life's ingredients are prepared. We would have to admit that the galaxy runs more than one kitchen, and some of those kitchens ship samples. Culture shock does not mean culture clash. Sometimes the outsider looks ordinary, and that is profound too. If the chemistry, dust mix, and activity all sit comfortably within our local bands, we learn that nature's recipe for small, icy worlds is robust across neighborhoods. That would strengthen the case that planets everywhere start with similar starter kits. If, on the other hand, the outsider stays delightfully unruly, then every anomaly becomes a new knob to tune in our models. Either outcome is a win because curiosity cashes both checks. Keep the humor handy. Earth may be the rock that won the cosmic lottery. Interstellar comets are the surprise guest who asks, "Do you season your comets like this on purpose?" When 3IATLAS shrugs off our expectations, it is not being rude. It is handing us an updated style guide for how the galaxy builds crumbs that later build worlds. Next, we change gears from curiosity to preparedness, asking how our watchfulness and playbook adapt when the visitor is not just unfamiliar, but unpredictable, and why building an intercept craft on permanent standby might be the smartest kind of impatience. Chapter 14, Planetary Defense, learns new moves. When a traveler barrels in from between the stars, it does not use our usual on-ramps. It does not politely merge from the outer cloud or follow the comfy lanes that our prediction maps love. It dives in on a line that slices the system like a surprise chalk mark. Planetary defense was built to watch regular trouble, asteroids that loop, comets that return, paths we can rehearse. An interstellar visitor forces the playbook to sprint, pivot, and invent. Good news, we can do that. Better news, the upgrades make us smarter for everything else too. First, tracking. Ordinary surveys Assume you can refine an orbit over weeks as more dots pile up. With a fast outsider, you do not get weeks, you get a handful of sleeps, and then the main act. So the first change is tempo. We move from leisurely confirmation cycles to a continuous handoff model, where discovery images, follow-up positions, and rough physical clues stream as a single thread. One team measures the wobble that tells distance, another measures color that hints at surface and gas, and a third refines a forward path every hour, not every few nights. Data does not loaf in an inbox. It sprints through automatic pipelines that spit out where to point next and how urgently. Think storm tracking, but for a rock with attitude. Next, the decision tree. Traditional hazard charts ask, will it come back? And will it get too close later? For an interstellar object, the question is different. What can we learn before it is gone? And could tiny non-gravitational pushes change a close and harmless pass into an uncomfortably closer one? The answer requires models that include gentle jets of gas and dust, because even small thrusters from sunlight, warmed vents, can shove the path. We bring those models out of the research lab and make them daily tools. The forecast becomes a band of futures instead of a single line, and our pointing plan covers the whole band, so there are no surprises lurking at the edges. Then come the new plays, rapid missions that can launch on the timescale of a news cycle. Picture a family of ready-to-fly spacecraft sitting fueled and sleepy, waiting for the word. Each one is small enough to ride as a hitchhiker on routine rockets, but with a punchy kick stage for the final sprint. The bus is modular. Swap a dust analyzer for a tiny spectrograph, attach a camera with a giant appetite for photons, or bolt on an aerogel collector that can sip passing grains without turning them into soup. The craft do not need to match the visitor's speed. They need to aim for a smart crossing and let the object fly through their field of view, turning a chance encounter into a planned flyby. Navigation is where the craft earns its coffee. A fast outsider is not going to wait while we phone home for steering commands. The spacecraft needs eyes and autonomy. Give it a star tracker that never sleeps, a narrow camera that can lock onto a faint smudge, and a guidance brain that can keep the target centered while the geometry changes by the minute. The craft should arrive with options: a close pass for high-resolution images, a slightly offset pass for safe dust collection, and a farther pass through the plasma wake for tasting the chemistry without risking a sandblasting. The pilot is an algorithm with manners. Sampling can be gentle. You do not have to land to learn a lot. A fly-through at the right distance turns the coma into a buffet. The collector opens for a precise window, swallows grains at speeds that a carefully chosen gel can handle, and snaps shut. A tiny mass spectrometer sniffs gas directly, reading out a menu before the count climbs too high and the instrument saturates. Downlink begins immediately. Even if the craft loses contact later, the first page of the notebook is already on Earth. Safe in multiple copies, that is not paranoia. That is how you respect scarce moments. Could we ever tag an interstellar object, as in leave a device attached? Only with grace. A gentle tagging concept would be more like a friendly sticker than a harpoon. A chip the size of a coin, spring ejected on a nearly matching path, might kiss the surface and cling with microspikes. It would not drill or shove. It would simply ride, broadcast its temperature, spin, and local chemistry until the battery gives up. If the geometry and risk do not line up, we skip the tag and do not apologize. The first rule of planetary defense is do no harm while you learn. Where do we stage these sprinters? Consider a craft parked near the sun, Earth Lagrange points, where the gravitational tides keep a satellite hovering in a slow dance with the planet. From there, the interceptor can pivot outward or inward quickly. Add a cousin craft in a high Earth orbit, and a third riding in the inner solar lanes, and you have a triangle that can pounce from multiple angles. Each carries the same interface for instruments, so a warehouse on the ground can keep a kit of add-ons ready: polarimeters, dust counters, fast spectrometers, even a tiny radar for surface texture. When an alert comes, a team rolls the right pallet to the pad. None of this works without people, and not just the usual suspects. Air traffic today includes citizen sensors and backyard gear that feed the discovery pipeline. For the defense layer, we fold in universities and small observatories as official nodes that can accept tasking within minutes. A clear night in one country can cover a stormy night in another. A string of modest telescopes can time brightness flickers that reveal spin states, which in turn tell the intercept craft where jets might push. The planet becomes an instrument because everyone holds a piece of the instrument. Why go to this trouble for a visitor that is almost certainly harmless? Because agility is insurance. A system that can race to meet a stranger can also handle homegrown surprises with more skill. The existence of ready interceptors pushes down the response time from years to months, from months to weeks, and from weeks to days for the simplest passes. Earth is basically a rock that won the cosmic lottery. Insurance is how you keep spending your winnings wisely. The dream endgame is a standing interstellar intercept program, a couple of nimble spacecraft always on alert, a menu of instrument kits, a global network that can flip from coffee to action without drama, and a pipeline that turns raw light into confident decisions. We might only get a handful of these visitors in a lifetime, but each one can pay for the whole system by upgrading our models, sharpening our sensors, and teaching us how strangers move. Next, we step into a spicier arena, the line between natural and artificial. How do you tell geology from engineering at interstellar speed without jumping to conclusions? Chapter 15 walks that tightrope. Chapter 15, the alien hardware hypothesis. There is a moment in every skywatcher's life when the data whisper, that is odd. The object brightens at the wrong angles, spins like a tossed book instead of a neat baton, or glides away as if sunlight is giving it the gentlest of shoves. Cue the spicy question people love and scientists dread. Could it be artificial? The right answer is neither a breathless yes nor a grumpy no. It is a calm checklist. Natural versus engineered is a diagnostic problem, and diagnostics begin with the ways an object moves, reflects, warms, and sheds material. If it is natural, it will teach us new tricks. If it is not, well, we will cross that astonishing bridge with both eyes open. First, motion. A visitor's path through the sun's pull is mostly a gravity play, but tiny, non-gravitational nudges can add up. If the object is venting gas, you get gentle thrusts that bend the path. If sunlight pushes a surface with a very high area compared to its mass, you also get a small shove. Scientists read this by comparing where the object should be under gravity alone to where it actually is, night after night. The offset is not a belief, it is a measured drift. Then comes the fork in the road. Does the drift match what outgassing would do at that distance from the sun? Or does it fit the fingerprint of sunlight pressure acting on a low weight, broad shape? Both are natural possibilities. One is the slow sigh of ices turning to gas. The other is a featherweight shard left from a breakup or a super porous sheet of dust welded by time. Rotation is the next clue. Many comets spin with a rhythm that slowly changes as jets act like tiny thrusters. Rocky fragments tumble in ways that can be predicted by their shape, if you have enough brightness data. What raises eyebrows is non-repeatable chaos or abrupt flips that imply external torques without obvious jets. But even that has natural options. Sunlight can torque irregular objects over time. Impacts by grains can tweak spin states. Internal mass shifting in a loose rubble pile can change the wobble. We test each by watching the light curve, how brightness rises and falls as different faces turn toward us. If the curve shows tidy periodicity, we infer a stable spin. If it shows a drifting pattern, we look for seasonal heating or jet geometry to explain it. Only when gentle, known torques fail do we consider stranger ideas. Reflectivity and color arrive like polite interrogators. Natural surfaces advertise texture and composition. Fresh ice is bright and blue-toned. Dustier crusts run darker and redder. And metallic minerals have their own muted signatures. An object that reflects light very efficiently at certain angles could be polished frost, thin crusts of salts, or highly porous foam that scatters light forward. Polarization helps. If the reflected light lines up strongly in one direction, it often points to tiny grains or layered surfaces rather than slick metal. A mirror-like glint would be dramatic, but even that is not proof of hardware. Flat crystals and fractured ice can throw knife blade flashes when the geometry hits just right. The job is to test mundane explanations first, and there are many. Thermal behavior is a quiet powerhouse, warms something, and it radiates. How fast it heats and cools tells you about density, porosity, and material. A hollow shell warms quickly and cools quickly. A solid hunk lags. Instruments sensitive to infrared light can watch the temperature lag behind sunlight and deduce whether the skin is fluffy, like frost, or tight, like rock. If there is outgassing, you will often see a mismatch between heat and brightness, as jets loft dust that reflects without much warming. If there is no gas, but the path still drifts, the needle points back to sunlight pressure and shape. Gas is the easy giveaway when you can see it. Spectra reveal telltale fragments that bloom when sunlight breaks molecules apart. If no gas is detected, that does not kill the natural case. Some ices are shy, and small objects do not always vent loudly. But a strong non-gravitational push, without any plausible gas signature, is where imaginations perk up. Before anyone reaches for the word machine, investigators try for ultra-sensitive searches of faint species, look for dust too fine to see, except in polarization, and model exotic ices that might hide their tracks. Nature is a better magician than we are. Radar, when possible, is a blunt truth teller. Bouncing radio off a target can sketch size and sometimes reflectivity. Highly specular returns would be surprising. Most natural bodies scatter radar like pebbled leather, not like chrome. But radar chances are rare for fast, faint visitors, so we usually rely on light alone. That means patience. Many nights, many angles, many instruments. A single weird measurement is a story starter, not a conclusion. So where does the alien hardware idea fit responsibly? It is a hypothesis of last resort, kept on the shelf for when natural catalogues are exhausted and contradictions stack up. Even then, it has branches. Engineered could mean a shard of something once large, drifting and dead. It could mean a device that does nothing but coast. It almost certainly does not mean blinking lights and radio beacons. The universe is under no duty to make our lives cinematic. The duty we do have is to build tests that would separate engineering from geology in principle. Could an object exhibit a reflectance spectrum with narrow features that scream synthetic lacquer? Could its thermal inertia be so low that only a membrane would fit? Could its spin stabilize in a way that suggests active control? Each of those would demand extraordinary evidence and extraordinary cross-checks. Here is the twist I promised. Even if the answer is natural, chasing these diagnostics upgrades our entire toolkit. Learning to detect the gentlest sunlight push teaches us to weigh objects by their area to mass ratio. Reading polarization at ridiculous precision trains us to separate fluffy from glassy grains across the sky. Building fast spectrographs that can sniff faint gases on a deadline prepares us to study newborn comets and dying asteroids with equal skill. The alien hardware hypothesis, handled with discipline, is a research exercise that pays off no matter what. Curiosity is the engine, caution is the steering. Keep the humor within guardrails. Earth is the rock that won the cosmic lottery. Science is the part where we do not blow it on wild guesses. Black holes are for deleting browsing history. Magnetospheres are pop-up blockers with pretty wallpapers, and interstellar visitors are prompts to update our investigative software. If the cosmos hands us a riddle, we show our work. Next time, we widen the lens from gadgets to seeds. The idea that dust and ice can ferry complex chemistry between suns, and how one grain from 3IATLAS could expand the recipe book for the origins of life. Chapter 16, Seeds Between Suns. Imagine the galaxy as a neighborhood where everyone's dry events send lint into the same alley. Not glamorous, sure, but surprisingly informative. Protoplanetary disks shed grains, comets shed grains, collisions make powder. Stellar winds and gentle nudges from light carry that dust between systems like postcards without stamps. Panspermia, the idea that life's ingredients and maybe hardy microbes ride these dusty postcards, has lived on the fringe and in the lab notebook margin for ages. Today, it earns a spot on the main page, not as a declaration, but as a question worth instrument time. Are solar systems quietly trading seeds, and did we finally remember to check the mailbox? First, the postage. A grain that can cross the gulfs must survive long, cold travel under harsh radiation. That sounds like a non-starter until you look closely at what dust can be. Many grains are not single crystals, but clumpy aggregates, little cathedrals of pores and plates. Pack organic molecules or microbial spores inside those nooks, and the outer layers act like a sun hat and a raincoat, blocking radiation, absorbing hits from charged particles, and keeping the interior dark and cold. Cold is not the enemy here. Cold can be a freezer. The challenge is time and shielding, and nature is very good at building foam from rock and ice. Next, the launch. How does a grain leave home? Catapult it with a cometary outburst. Lift it gently with starlight pressure. Blow it outward with a star's steady wind. A newborn system, full of newborn planets, is basically a construction site. Debris flies. Some of that debris inevitably reaches escape speed, and a fraction of that debris is small enough to ride radiation pressure, yet large enough to keep a protected interior. Most grains will wander forever and do nothing dramatic. That is fine. We only need a rare few to wander into a new system's traffic and get slow enough to be caught. Then, the delivery. A grain sailing into a new planetary system has several doors to try. Gas giants offer strong gravity that can bend paths and store grains in cold corners. Comets and asteroids can sweep them up and carry them inward later. And there is always the gentle rain into atmospheres. High altitudes are surprisingly kind. A particle, smaller than a grain of pepper, can float downward in slow motion, warming gradually, shedding its outer soot, while keeping the core intact long enough to reach layers where chemistry can start talking to chemistry. What would it mean if the seeds are only ingredients rather than organisms? That alone would be a big deal. Complex organics that form on dust surfaces in distant clouds could set the starting conditions for planet chemistry across many systems. Deliver those molecules onto warm, wet worlds, and you hand them a head start. Pre-mixed syrups of carbon chains, rings, and delicate structures that lab experiments already know how to build when ice, dust, and light team up. In that picture, panspermia is less a stealthy contagion and more a galaxy-wide grocery service. And the spicier possibility, microbes. Some earthly microbes shrug at dryness, salt, and low temperature, folding themselves into tiny, stubborn packages that wake when conditions improve. A few species tolerate radiation doses that would make electronics cry. No one is claiming that such adventurers have crossed interstellar space. The question is whether it is physically absurd or physically rare. Rare is not never. For this to move from speculation to testable science, we need experiments that expose spores tucked into mineral foams to long baths of simulated space radiation and then test for survival. We also need clean sampling above Earth's messy lower air to look for particles with a suspicious mix, extraterrestrial mineralogy outside, fragile organic scaffolds inside, and a structure that argues for assembly in cold, shielded environments rather than in our atmosphere. How would you tell a true interstellar seed, ingredient, or organism, apart from local fluff? 3 families of tests lead the way. First, chemistry at high resolution. A seed built in a different nursery could show unusual ratios of isotopes in elements like hydrogen, nitrogen, or carbon, subtle tilts that trace a different temperature history. Second, handedness tests. Many organic molecules come in two mirror image forms. Life on Earth prefers one hand for certain families. If you find a bias that does not match our usual pantry, you raise your eyebrow. Third, structural context. A grain that encloses organics in layers consistent with growth on dust under ultraviolet light, then burial under fresh ice, tells a story that is hard to fake in the lower atmosphere. Where do we go hunting? High in the stratosphere, with collectors that fly above most contamination on suborbital hops that open a door, taste, and bring a pristine sample back the same day, along the path of a known interstellar visitor, with a quick flyby probe that carries an aerogel panel to capture grains intact, inside the coma of a comet that has recently scooped up interstellar dust. Because comets are hoarders and might stash foreign mail in their freezers, even on the moon, where the most delicate organics would not last long in sunlight, but where a buried layer beneath regolith could archive a trickle of ancient dust for later excavation. The caution flag flaps loudly. Contamination is sneaky. We build clean rooms, we bake hardware, we include blank controls that fly the same flight but never open to the sky. If a detector screams life, we try to make it shut up by proving it wrong. Only when it refuses do we let ourselves grin. Science earns its fireworks by surviving its own water balloons. Now, the payoff if the answer is yes in any form. If interstellar seeds exist as ingredients, we learn that worlds form from a shared pantry, and origin of life chemistry might get a boost no matter which star you orbit. If hardy microbes occasionally ride the mail, we confront a galaxy where life's spark can travel, even clumsily. That does not diminish any world's uniqueness. It underlines how connected the neighborhood is. Either way, we gain respect for dust, the most underrated librarian in the cosmos. And the humor check. Photosynthesis might say we invented solar panels first, but dust would counter with we invented zip files for chemistry. Comets deliver, planets unpack, and the galaxy takes notes. In the next chapter, we leave microscopes and mass spectrometers for headlines and late-night conversations. Culture, curiosity, and cosmic perspective will show how a single outsider can rearrange the stories we tell ourselves about home. Chapter 17. Culture, Curiosity, and Cosmic Perspective. The night an interstellar traveler earns its name, people step outside with mugs and questions. You can feel the city exhale. Apartment balconies become pop-up observatories. Parks host polite clusters of strangers who whisper as if the sky could hear them better that way. Someone points, someone narrates, someone misidentifies a plane, and laughter resets the room. Earth is a small stage with very large binoculars. Sometimes the universe waves back, and our first impulse is to wave too. Headlines sprint to the front page with a familiar split personality, wonder and worry in alternating fonts. One corner asks what it means, the other promises what it does not mean, and a third column reminds everyone that we have done this before, just not often. The news cycle tries on metaphors like outfits, the messenger, the wanderer, the guest who will not stay for coffee. Language matters because it frames the feeling. A visitor is a story, an object is a statistic. We tend to choose story when the sky gets involved. Artists make the fastest pivots of all. Within hours, there are posters, pinhole camera prints, time-lapse tapestries that compress an entire night of motion into a gentle curve through city light. A choreographer watches that curve and builds it into a dance phrase. A poet hears the chorus of lawn chairs creak and writes about the orchestra of necks craning at once. Musicians lean into slow, sustained notes and call it a soundtrack for looking up. The universe does not endorse any of this, but it does not object either. Good art is a telescope for feeling. Backyards become classrooms. Parents explain orbits with oranges and lamps. A teenager with a tripod and a stubborn streak tries a 1,000-second exposure and discovers the thrill of stacking images. Teachers ask for 5 minutes at the start of homeroom so the class can see a simulated path on a projector and then vote on a nickname. The school librarian rolls out a cart of old astronomy books and finds every single one checked out by lunch. Science fairs sprout new projects overnight. Homemade star trackers, meteor microphones, even a neighborhood map of dark sky pockets rated by how many stars appear after midnight. There are debates, because of course there are. How much certainty do we need before we say visitor from elsewhere? What counts as responsible excitement when data are still blurry? Scientists try to be clear without being dull, which is harder than it sounds. They bring diagrams where arrows are straight and voices where caution is gentle. People listen, and most appreciate that patience is the opposite of buzzkill. Curiosity likes company, but not chaos. Communities with less access to dark skies speak up. The night of the first vigils, you can see the invisible barrier that streetlights draw. In the city core, the guest is a rumor. At the edge, it is a ribbon. The conversation broadens to light pollution, like a lens that will not focus. New pledges appear. Dimmer fixtures, later curfews for ornamental lights, local star parties scheduled to share the sky with neighborhoods that rarely get a clean view. Progress is small but real. A few bulbs come down, a few lamps point lower, a few kids see a tail for the first time and decide that the sky is not a screensaver. It is a place. Online, the memes do what memes do. There is the inevitable comparison to cosmic delivery services. There are jokes about the universe dropping by without texting first. One image earns 1 million shares, a coffee cup with star streaks reflecting in the surface, and the caption, "Leave room for stardust." Humor oils the gears of attention, keeping them from squealing under the weight of too many facts at once. Religious and philosophical voices find new timbers. Some see a sign, others see a reminder. Either way, the visitor pulls words like humility and stewardship back into the room. We write letters to the future, without being asked. We tell each other this is why we keep the porch light on, for the unknown. Even the most practical among us, the timers and schedulers, admit the night feels larger in a way that resists measurement. It is not just the object, it is the feeling of standing in the same posture across continents, looking up at the same moving dot, and understanding that distance and difference do not cancel that shared moment. Economies notice. Camera shops sell out of tripods. Libraries run workshops on how to borrow telescopes that were gathering dust next to travel guides. Small towns near dark stretches of highway host pop-up gatherings with hot chocolate and local bands. Tourism boards create maps of safe pullouts, labeled with times and bearings. The guest turns into a night market for wonder, and wonder turns out to be good for small businesses that know how to offer warm hands and clear directions. Science itself learns from the crowd. A flood of backyard data makes a global quilt. Some images are fuzzy, some perfect, and together they become a time machine, documenting how brightness rose and fell across hours the professionals could not cover. Volunteer coders build tools that tag, align, and share, then leave those tools up because the night will call again. The idea that knowledge is a team sport lands not as a slogan, but as muscle memory. With time, the visitor fades, the headlines slide down page by page, the lawn chairs go back to garages, but the after-image stays. A few people sign up for community college astronomy because of a night they will remember forever. A child keeps a sketchbook of crescent moons and clouds, and eventually studies weather because the sky refused to be a flat ceiling. A city passes a modest lighting ordinance and, 2 years later, counts a dozen more visible stars from the same park bench. Earth is still the rock that won the cosmic lottery. We still misidentify planes. We still argue about the best way to photograph a streak you can barely see, but our sense of neighborhood changes by a notch. The map gets a dotted line that says, sometimes the outside visits the inside, and when it does, the stage grows, the audience expands, and the applause sounds a lot like silence, because that is how space claps. In the final chapter, we will ask what changes stick after the guest is gone. New models, new missions, new habits, and imagine a world where spotting the next traveler is routine and our welcome wagon is already rolling. Chapter 18, After the Visitor. What changes next? When a traveler from between the stars fades into the dark, the real plot twist begins. The sky looks the same to casual eyes, but inside observatories and mission rooms, dials have been nudged and checklists rewritten. Models are not museum pieces. They are living documents, and tonight they get new verbs. The result is a quieter revolution. Detection becomes faster, interpretation becomes richer, and the whole solar system upgrades its welcome protocol from improvised to intentional. Earth is still the rock that won the cosmic lottery. Now it spends a little more of its winnings on foresight. Start with the models, the maps in our heads that tell us what a stranger might do under our sun. Before, we treated unusual paths as outliers. After, we fold them into the standard menu. Forecasts that once drew a single crisp line now draw bands of possibility that flex as fresh data arrive. Spin states, outgassing patterns, light pressure nudges, those stop being exotic footnotes and become sliders you can adjust without hunting for a specialist's phone number. The math gets friendlier, not because it is simpler, but because we have taught our tools to speak in everyday units. Point here, expect this brightness, watch for that tail behavior if the wind shifts. It is the difference between reading sheet music and hearing the tune. Missions change their posture next. Instead of drafting audacious proposals that spend years warming the bench, agencies keep one or two nimble craft fueled and stretch-ready. Interstellar intercept moves from a hypothetical to a policy, a standing capability with a small fleet identity, the way weather satellites quietly guard every forecast. Payloads learn to travel light, but think big. A single bus can carry a compact camera with a taste for faint light, a sniffing instrument that loves a good vapor, and a collector that treats passing grains like fragile postcards. Guidance brains practice on fast targets in our own backyard, asteroids, quick comets, so that when a true outsider is called in, the autopilot already knows the dance. Monitoring grows broader and more democratic. Wide field surveys stitch the sky nightly with fewer gaps, and the alert stream that once felt like inside baseball now reads like a public traffic map. Citizen science is no longer a friendly add-on, it is a designated lane. Backyard telescopes register for tasks the way rideshare cars accept pickups. Timestamps are precise, color calibration kits are cheap, and short training videos turn a curious person into a reliable node in an afternoon. The sky becomes a cooperative grid where professionals and amateurs pass the baton without dropping it. We also learn to archive like librarians who have seen the flood. Every image, spectrum, and timing mark lands in a repository that knows how to tag by event, geometry, and instrument temperament. The quiet genius here is comparability. When the next visitor appears, we can place 2 nights from this year against 2 nights from 5 years ago and know we are comparing apples to apples. That is how a map of the galaxy's chemistry begins, not with a single spectacular detection, but with a steadily growing shelf of well-labeled jars. Each interstellar traveler is a new dot on that map, a new data block in the quilt that says these ingredients are common, those are rare, and here is how sunlight teaches both to glow. Education absorbs the ripple and codifies it. High school labs add a unit where students simulate a visitor's path with real sky coordinates and plan a one-night campaign. Community colleges host pop-up workshops on how to catch faint spectra with off-the-shelf gear. Museum planetariums rehearse the next alert with scripts that will flex to the actual sky when the night comes. We do not wait for inspiration to strike. We schedule it. Policy follows tastefully behind. Open alert standards become law within the astronomical community. If you find it, you share the minimal essentials fast, and you share them in a format that robots can read. Launch windows for rapid missions get reserved the way disaster relief air corridors do. Rarely used, instantly available. Modest dark sky ordinances earn a new argument. Not only do stars matter to culture, they matter to a planetary sense and response system that protects and informs. Some changes are small but sticky. Observatory control software keeps a visitor mode that bundles settings for faint, fast movers. Data dashboards remember which instruments performed well last time and pre-suggest similar lineups. Even the way we tell the story matures. Newsrooms keep a how to watch responsibly template that balances wonder with context. We stop treating each appearance as a singular miracle and start treating it as a chapter in an ongoing correspondence with the wider galaxy. The most charming upgrade may be philosophical. After you have watched one outsider alter your tools and habits, you start expecting the next knock at the door. That expectation trims a little fear and grows a little hospitality. We build for continuity. We teach that not all cosmic events are one-off spectacles. Some are recurring invitations to refine attention. Curiosity becomes a maintenance plan. Picture the near future on a clear night. A survey pings. Fast mover, inbound on an unusual line. Within minutes, a ribbon of small satellites swivels for a first look above the weather. A ground network syncs exposure plans across half a dozen continents, and a waiting interceptor nudges off a parking orbit, already thinking about which side the sunlight will favor. Kids in a school gym stream a live dashboard. A backyard scope packet hums over a neighborhood mesh. Hours later, first spectra arrive. The global model narrows its band of futures, and observers everywhere see their screens bloom with tiny green lights labeled confirmed. No panic, no scramble, just a planet taking attendance. Fast forward further. The map of the galaxy's chemistry is no longer a sketch. It is a seasonal atlas that updates after each guest. We can say with a straight face that carbon chains of a certain length show up often, that certain nitrogen patterns are common in colder birth clouds, and that lightweight, fragile grains carry surprises if you catch them before sunlight edits them. We stop guessing which kitchens bake what and start citing the house styles of distant neighborhoods. And the tease because curiosity likes to set a table. We met a traveler. Next time, we might send a welcome wagon. Not a grand flagship, but a tidy, thoughtful emissary that can match pace, speak in instruments, and leave behind a beacon that says we noticed, we learned, and we will be here when your cousins pass through. The next series will sketch that craft from nose to tail, propulsion, sensors, etiquette, and imagine the first handshake we design on purpose.